Okay, so let's first start by talking about what energy is. So I feel like the majority of lectures and any type of science that you deal with always has some sort of slide that defines what energy is. Okay, so what is energy? Energy is the capacity to do work, right? So that's great. That's what energy is. But what is work exactly? So work is taking something like a box and applying a force and moving that through a distance. Okay, so work is force acting over a distance. Again, when I have to push this table across the room, that is me doing work, right? Again, energy is the capacity to do work, so I have lots of energy. All right, so what types of energy do we usually deal with? Okay, so there are a couple of different types of energy, and we're going to talk about them. So one type of energy is called potential energy, and that is the energy that is associated with the position or the composition of an object, right? So if I had a big weight, a nice little 10 kilogram weight at the top of the building, what does it have a lot of? Potential energy, right? So it's got a lot of potential energy, and again, this is the energy that is associated with the position of it, right? It's really high above the building, it wants to fall to the earth, okay? So another type of energy that we frequently deal with is kinetic energy, right? This is the energy that is associated with motion. If I push my little weight off the building, it had a lot of potential, what's going to happen to that potential energy? It's going to turn into kinetic energy, right? It's going to turn into the energy of the motion of the weight falling to earth, okay? So just in general, with respect to potential energy, what do we always want to try to minimize with respect to mechanical systems? Are weights that hang above the earth, are those super stable? No, right? So with respect to energy, systems always tend to a minimum of potential energy. The weight falls to the earth because it has a minimum of potential energy at that point in time. When it hits the earth, it's very little potential energy. A lot of that has been transformed in the form of work. Transferred in the form of work with respect to the ground. Okay, so again, potential energy is the energy associated with the position of an object, whereas kinetic energy is the energy associated with motion. Okay, so another type of energy that we encounter with respect to chemistry is something called thermal energy. Okay, so thermal energy is the energy that is associated with the temperature of a substance. Okay? All right, so with respect to thermal energy, there is kind of an overall understanding with respect to thermal energy transfer. So things that are considered hot, so let's say we have a coffee here, we consider it very hot, it has a lot of thermal energy, right? So this has lots of thermal energy. So lots. Let's say I have my hand doesn't have a lot of thermal energy because it's fairly cold. Okay, so I've got my hand, I don't want to draw it because I can't draw hands, so it's fairly cold, there's not much thermal energy. If I touch my hand to the hot cup, what's going to happen? There's going to be a transfer, right? There's going to be a transfer of thermal energy from what to what? To the cup to the hand. So in terms of temperature, right, we're seeing a transfer of thermal energy from things with high temperature to things with low temperature, right? Have you ever observed a different process where you touch something that's hot and it just sucks out energy out of your hand and it becomes even hotter? No, right? So this is kind of just like with respect to potential energy, just like the minimum of potential energy, this is kind of like just a law of nature. You're always going to see thermal energy transfer from things that have hot to cold. So just like we saw with respect to potential and kinetic energy, we transferred that energy in the form of work. With respect to thermal energy, this transfer is going to come in the form of heat. So that's what we define as heat, is this actual transfer of thermal energy from things that are hot to things that are cold. Okay? Again, that transfer is via heat. Does that transfer happen forever? So again, if I have my cold hand and I touch this hot coffee, is that going to continue forever? When does it stop? When the temperatures of the two are equal to one another, right? So when they have the exact same final temperature, then we have come to a point which is called thermal equilibrium. Okay, so again, we'll see this transfer from things that are hot to things that are cold until both things have the exact same temperature, and we are at thermal equilibrium. Okay, so that is another type of energy. So we've got potential, kinetic, thermal energy. One more with respect to chemical reactions and chemical systems is what we call chemical energy. So chemical energy is kind of like a form of potential energy. So with respect to mechanical systems and potential energy, potential energy always had to deal with the position of an object, okay? With respect to chemical energy, this is going to be energy that is associated with the positions of electrons and nuclei in various chemical species, various substances, okay? So with respect to chemical energy, we're looking at the energy associated with electrons and nuclei in our atoms and molecules. And the best way to kind of illustrate what we mean by this chemical energy is via what we call electrostatic energy. Okay, so in electrostatic energy, we kind of model this idea based on something called Coulomb's law. And this energy, or electrostatic energy, is kind of a derivative of Coulomb's law. What we're looking at here, though, is the energy with respect to two charged particles. Okay, and so we've kind of talked about various ramifications of this with respect to electrostatic interactions. So let's imagine that we have some sort of salt, something like NaCl. Right? So again, we're dealing with the chemical energy that is associated with the attraction between these two. Okay? We model this attraction via this electrostatic potential energy. So let's imagine that we have our sodium next to our chloride. Okay? And they are separated by some distance r. So when we put these guys into our little Coulomb's law, when we model them with this electrostatic potential energy, the Q's are referring to the charges. Okay, so Q1, Q2 is referring to the two charges between our two various atoms that we're dealing with. Okay, so for sodium chloride, what are the magnitudes of my charges here? +1 and -1. So I'm going to ignore right now the K because it is just a constant. When I put this in here, for the sodium we have a +1, for the chloride we have a -1, and this is going to be separated by some distance, and this is what we're referring to as R here. Okay? So again, we always want to minimize energy. Same thing with potential energy. Okay? As we bring these two closer together, what's going to be the magnitude, or what's going to be the sign of their interaction? Are they going to be positive or negative? It's going to be negative, right? So overall, we have a negative, so we're decreasing the potential energy. And what's going to happen to the magnitude of this negative value as we bring them closer together? So as this guy gets smaller, this is going to get bigger and more negative, right? So what we see is, again, this minimization of energy as we bring these two charged particles closer together. So this is how we kind of represent this idea of chemical energy. To take these guys farther apart, we're going to have to supply energy to do that, okay? But again, we kind of idealize chemical energy in the form of electrostatic energy. Okay, so potential energy, kinetic energy, thermal energy, and chemical energy. Those are all our various energy types. So now we're going to introduce you to the law of conservation of energy. This is very similar to the law of conservation of mass. So with respect to mass, what do we know about a chemical reaction? Can we create or destroy matter? No. So the exact same thing is going to happen with respect to energy. So in a chemical reaction, or in any type of process, energy can neither be created or destroyed. Okay? It can be transferred, though. Right? So what is one way that we have been transferring energy thus far in our discussion? So again, if I had, let's say, a nice little billiard ball on my table, and this guy was in motion, had lots of kinetic energy, and it was going to collide with this guy at rest, what's going to happen to the one that's at rest when the collision occurs? It's going to move, right? It's going to flow down the table. That was transfer of energy, but how did we do that? What transferred that energy between the two? That's the definition of work, right? Force through a distance. When this guy hits this guy, it transfers its energy, force through a distance. And so we can transfer energy in the form of work. So that's one way we can transfer energy between two different things. What was the other way? Put my hand on that hot cup of coffee. How did it transfer its thermal energy to me? Thermal, but what do we call that? That transfer of thermal energy was heat. So two ways that we can transfer energy is via work and heat. Okay, again, they don't disappear. The energy doesn't disappear. It just goes from one thing to another, again, via work or heat. It can also assume other forms. So what do I mean by that? If I have another little billiard ball and I have it high up in the air and I drop it, it's got lots of potential energy, right? Just like the weight on the top of the building. When I drop it, what happens? What happens to all that potential energy? Turns into kinetic energy, right? So this is what we mean by assuming other forms. When we drop this, all of this potential energy becomes kinetic. So again, energy does not get created or destroyed, it just takes another form. Okay, so we can transfer it via heat or work, or it can be essentially transformed into kinetic energy. Okay, so that is the law of conservation of energy. Now this is going to introduce us into the first law of thermodynamics. So thermodynamics is a topic that we will come back to eventually in 116. So in the second semester of general chemistry, thermodynamics is essentially going to provide us the means by which we can determine whether anything ever happens at all. Okay, so it's got this big grandiose idea behind it. We're kind of constrained in this first semester of chemistry to only talking about the first law, but again, there's more laws and we will come back to them. All right, so the first law of thermodynamics tells us that the energy content of the universe is constant. Okay, so what is the universe first off? If you imagine what the universe would be, what would you think of? Is there something outside the universe? No, right? So the universe is everything, right? So that's what we should first assume. Number one, the universe is everything. Okay, so total energy of the universe is constant, right? So this comes back to the law of conservation of energy. We know we can't create or destroy energy. It can assume other forms, we know that. It can also still be transferred, right? So if the universe is everything, is there anything with which the universe could transfer energy with? No, right? And so because there's nothing outside of the universe to transfer energy into or out of, that tells us that the total energy content of the universe is constant, okay? So you can't just make up energy. It doesn't happen like that, okay? All right, so again, what does this mean? If you are using energy right now, which you are because most of you are alive at this point in time, you're using energy to maintain that system far away from equilibrium, it has come from somewhere, right? It can't just come out of nowhere. There is no such thing as a perpetual motion machine. So for example, I am using energy to talk in front of you at this point in time. Where is this energy that I'm using? Where did it come from? Food, right? So I had a Starbucks breakfast sandwich this morning. That was number one. I also have lots of stores that I can rely on in case of starvation. That's number two. Where did the food that I ate come from? Plants, right? So I eat cows sometimes. They eat grass. Where did the grass come from? Where did it get its energy? From the sun, right? And something happens in the sun. It's like some sort of thermonuclear thing where energy is generated. But again, the purpose of this is that if you're ever using energy, it has come from somewhere. Okay, so you can't get something for nothing in terms of energy. All right, so that's great. First law of thermodynamics, the energy content of the universe is constant. It has a very nice, pleasing ring to it. It's a nice little law to live by. Okay, so with respect to energy changes, sometimes it gets confusing whether or not energy has been created or destroyed, right? So what we utilize when we are tracking energy is we utilize a system called the system and the surroundings, Okay, so the thing that we are interested in an energy exchange is what we call the system. So this could be our chemical reaction, it could be the billiard ball that we're watching, etc. Okay, so whatever we are interested in, we define as the system. Everything else with which the system can exchange energy with is what we call the surroundings. Okay, so again, this is anything our system can exchange energy with. Okay, system and surroundings. So together, what do you think they make up? So system, which is what we're interested in, surroundings is anything it can exchange energy with. Together, combined, what do you think they constitute? The universe, right? System and surroundings make up our universe. All right, so whatever happens to one, the big idea behind tracking this is whatever happens to one is going to be the opposite of what happens to the other. Because again, we're exchanging energy between our system and our surroundings. Okay, so there are a couple of different types of systems depending on what can be exchanged between them. So the first type of system that we defined is something called an open system. So in an open system, we can exchange both energy as well as matter with our surrounding. Okay, so open systems exchange energy as well as matter with their surroundings. A good example of open systems would be humans, right? We can exchange energy with our surroundings. If you touch something that's cold, we're transferring energy. What about matter? Do we exchange matter with our surroundings? Yes, right? We eat and we breathe and we do other things, right? So we can exchange both energy and matter. Another type of system that we will deal with is something called a closed system. So in a closed system, we can exchange energy, but we cannot exchange matter. So no matter with the surroundings. So this is only energy. A good example of a closed system is something like this, something like the piston that's in your car. So in the piston in your car, and I don't know how cars really work, I know there's an expansion, right? There's an expansion of a piston because of gases. This is a system where you can't actually exchange matter. The matter is going to stay in the system, but it can exchange energy in the form of doing work by expanding against that piston. Okay, so closed systems don't exchange matter, but they do exchange energy. And then finally, isolated systems cannot exchange either one, right? So in isolated systems, we can exchange energy, and we cannot exchange matter with the surroundings. A good example of an isolated system, in theory, idealized, something like this, something like a hydro flask, right? Closed, sealed hydro flask. What is the purpose of this? Why do we use it? Keeps everything cold, right? Why does it do that? In theory, in the idealized perfect version, where nothing leaks out, it's not exchanging any energy with the surroundings. So everything in there is kept cold, right? Again, this isn't perfect. If you put a bunch of ice in here, is it going to melt eventually? Yes. But again, the purpose of this, idealized, is to not be able to exchange any energy with the surroundings. That's why they produce the little vacuum seal on the outside. And if it's sealed, then it can't exchange matter. So that would be, in theory, a perfect isolated system. Okay, all right. So a couple more slides, and then I'll let you guys go for the day. Now that we have defined our types of systems, we need to talk really quickly about energy units, right? So this is a new thing that we've talked about, energy. So we need to define how we specify the amount of energy, what our units are for energy. So the unit of energy comes from the equation for kinetic energy. Does anyone know what kinetic energy, what the equation is? 1/2 mv squared. What does m stand for? Mass. So m is mass. And in the SI system of units, what is our SI unit for mass? Kilogram, right? So don't be confused. The SI system for mass is the kilogram. What is V? What is V supposed to be referring to? Velocity, right? So how do we measure velocity in SI? meters per second. It is a derived unit. So what this gives us, when we put this in for our kinetic energy equation, is 1 kilogram times meter squared per second squared. That is defined as the joule. We give this the capital J. So joule is how we measure energy with respect to SI. Okay, so the joule is actually very small with respect to the amount of energy. It's a small little value. So frequently, we will be dealing with things like kilojoules. Okay, so what do you think of kilojoules with respect to a joule? For every 1 kilojoule, how many joules do you think we'll get? 1,000 joules. So that's what's great about the metric system, right? It applies regardless. So kilojoules is just 1,000 joules. Another common way that we measure energy, unfortunately, is something called the calorie. Does anyone know what a calorie is? Tiny little c? I think this is like an English convention, like a biological thing. Little calorie is defined by the amount of energy it is required to raise the temperature of 1 gram of water 1 degree Celsius. Okay, so that's where we get our tiny little tiny calorie. In converting to joules, just note that 1 calorie is equal to 4.184 joules. You should know that conversion, just in case. What about the big C, which is what we utilize when we look at our nutrition information? What does the big C refer to? Kilocalories, right? So 1 big C is equivalent to 1,000 little calories, right? So this again illustrates why the metric system is so much more preferable, right? This prefix makes sense. What if my handwriting, which it is very bad, what if I tried to write big cal and I wrote little c, or you thought it was little c? How foolish is that? Why would 1,000 little c's be a big C? I don't understand that. It doesn't make any sense to me. So this is why this is not a smart system to go with. Okay, so then one more, kilowatt hour. It's another measure of energy. Where will you find a kilowatt hour usually? Things to do with electricity for the most part, right? So if you look at your electricity bill, you usually see how much energy you utilize in kilowatt hours. So note that 1 kilowatt hour is a gigantic amount of joules. How much money does 1 kilowatt hour cost-ish? Estimated, let's just say 30 cents, right? So again, 1 little tiny kilowatt hour, which is pretty cheap, it's only 30 cents, is equivalent to a gigantic amount of joules, okay? So this is again just trying to illustrate how tiny of a unit the joule is. Okay, all right, so those are units. What else? I'm going to take 10 more minutes, I promise. That's it. A couple more things. Okay. Internal energy. Let me get my little pencil back. I'll forget it. Okay, internal energy. We're going to define, or we're going to start talking about the energy that is important with our chemical reactions. And we start this discussion by introducing this concept of internal energy. So internal energy is defined as the sum of all of the energies of the system that we're dealing with, right? We're usually always interested in our system. And for chemistry, our system is almost always some sort of chemical reaction, okay? We define the internal energy of our chemical reaction as the sum of the kinetic and potential energies of the system, of our reaction, okay? Frequently what we will find is that the absolute value of internal energy is something that we can't obtain. Instead, we usually determine how internal energy changes in the overall process of a chemical reaction, okay? So we're going to be interested more in this change in energy, this delta E, as opposed to just E by itself. Okay, so now, internal energy is what is called a state function. And I'm going to kind of highlight what a state function is for a while because it's kind of important that you understand its definition. So for a state function, we define a state function as anything, any type of thermodynamic function whose value only depends on the final and the initial states of the system and not on how it got there. Okay, so I'm going to try to illustrate this via a nice little example. So, comparatively, altitude the measurement of altitude is also a state function, right? So when we measure altitude, again, we're frequently interested in changes in altitude. And I'm telling you that with altitude being a state function, the change in altitude for any type of reaction or any type of person is only going to be dependent on the final and the initial altitudes of that person and not on how they got there. Okay, so let's use an example to try to illustrate that. Let's say we have a hiker, right? And this hiker, we'll call this hiker A. It's at the base of a mountain, right? So initial altitude here for our little hiker, altitude initial is 0 feet. Hiker A is smart, right? Hiker A just hikes up the surface of the mountain and it gets to the top of the mountain. Nice little hiker A, where the altitude is 10,000 feet. Right? So if I wanted to calculate the change in altitude for hiker A, what would I utilize? Again, change in is final minus initial. And so if I wanted to calculate my change in altitude for hiker A, what values would I use? What is my final altitude? 10,000 feet minus my initial altitude, 0. So we get an overall change in altitude of 10,000 feet. So again, hiker A is smart, okay? All right, so now let's compare this to hiker B. Hiker B is not smart. So hiker B is on the other side of the mountain, same initial altitude, so same initial of 0 feet. Well, let's say hiker B intention is to go to the top of the mountain. Hiker B starts, and let's say hiker B gets up to about 3,000 feet. Okay, so hiker B gets up to 3,000 feet and then remembers or drops or realizes that hiker B dropped its water at 1,000 feet, right? It needs its water to get up to the top of the mountain. So what is hiker B going to do? It's going to climb back down, right? It's got to go get its water, right? So we're at 3,000 feet, and hiker B climbs back down to 1,000 feet to pick up its water, okay? Once hiker B does that, now he's ready to climb up to the top of the mountain, and so he does so to 10,000 feet, okay? So now hiker B took a different path, right? And this path has 3 separate segments to it. It has segment 1, it has yellow, which is segment 2, and it has red, which is segment 3, okay? So we're going to look at the overall change in altitude for hiker B. So for hiker B, we'll go with black. We have 3 separate segments that define its change in altitude. We have segment number 1, we have segment number 2, and we have segment number 3. What is my overall change in altitude for segment number 1? What was my initial altitude? 0. What was my final altitude for segment 1? 3,000, right? So we 3,000 final minus 0. We're going to add that to the change in altitude for segment 2, right? So we started at 3,000 feet and then we climbed back down to 1,000. So final here is 1,000 minus initial is 3,000. And then we're going to add that to our little segment 3, which we started at 1,000 feet and then hiked up to 9,000 feet. So 9,000 is, or 10,000, pardon me. 10,000 is our final, minus 1,000 is our initial. So when we add all these guys together, we're going to get 3,000 minus 2,000 plus 9,000. What is the overall change in altitude for hiker B? It's the exact same thing. It's 10,000 feet, right? So this is what we mean by a state function. It does not depend on the path that he took, right? He could have gone up and down and up and down. All we care about is where you start and where you end, okay? Internal energy is also a state function. Its path is not going to depend, or its value is not going to depend on the path that it takes, only on its final and its initial states. Okay. All right, so that's it. I'm done. I can't anymore. So then if I record, I don't want to mess. Functions. So we introduced you to state functions because internal energy is also a state function. So what was internal energy? How did we measure internal energy? So we represented it by this big capital E, right? this was a sum of both the kinetic energies as well as the potential energies of our system. So it's all of the energy that's contained in a system. That's how we define internal energy. All right, so just like altitude, internal energy is also a state function, right? So its value or its change in internal energy is only going to depend on the final and the initial states of the system and not on what path we took to get there, okay? So in a chemical reaction where we have reactants going to make products, what's the final state of our system? Who do we call the final state? What do we end up at? Who? Reactants or products? Products, right? So for internal energy with respect to our chemical reactions, the products are always the final state of our system, whereas the reactants are going to be the initial state of our system, okay? And so if we wanted to measure this change in internal energy in a chemical reaction, then we would need the internal energy of our final state, which is our products, and then we would subtract the internal energy of the initial state, which was our reactants. So, nope. Reactants, okay? So anytime we want to determine the change in internal energy of our system, all we need is the internal energy of our products, internal energy of our reactants, and we don't need to know the method or the path by which we took to get to both our final and initial states, okay? Okay, so let's look at these signs with respect to change in internal energy depending on the types of reactants that we have. Products and types of reactants that we could see, okay? So let's say that we have a reaction, something like carbon combining with oxygen to form CO2, okay? And we're letting this reaction occur, right? So we've got our reactants, we have our products. And in the process, we want to measure this change in internal energy in going from our reactants to our products, okay? So for this reaction, what we find is that our products, so the internal energy of our products, is actually less than the internal energy of our reactants, okay? So these guys, our products, our CO2, has a less value of internal energy than the two reactants. If I'm looking at the change in internal energy for this reaction, what is going to be my sign? If products have a smaller value of internal energy than reactants. So here we're going to have a smaller value that comes first minus a larger value. So overall, what is going to be the sign of this change in internal energy? Negative, right? So if we do have a reaction where our products have a lower internal energy than our reactants, then we're going to have this overall negative change in internal energy, okay? When we're talking about this guy, we're always talking about the system, or most importantly, our reaction. So our reaction loses internal energy, right? Where does that internal energy go? Because we can't just destroy it. Where does it go? So if our reaction is our system, then what's everything else? Surroundings, okay? So we have a system where, again, we're going to lose internal energy. We're going to have a negative delta E, then that energy is going to go to the surroundings, okay? All right, so now what if we reverse this reaction? What if we took this reaction and we reversed it, right? So now we have CO2 as our reactants, and we have carbon and oxygen as our two products, right? They still have the same internal energy amounts, right? So now we have a situation where the internal energy of our products is actually greater than the internal energy of our reactants, okay? What is going to be the sign for this change in internal energy if the products have more internal energy than the reactants? It's going to be a positive value, right? So what this means is that our reaction, in doing this, is going to take in internal energy from where? The surroundings, right? So we have to gain internal energy for this reaction to go, and that internal energy is going to come from the surrounding, okay? So just as a general principle, whatever happens to our system, our reaction, is always going to be the same exact magnitude but opposite sign of whatever happens to the surroundings. If our system takes in energy, then the surroundings have to lose it, so they're going to have a negative sign. If we lose energy, then the surroundings are going to gain it, so they're going to have a positive sign. Okay? Okay, so now, going back to the law of conservation of energy, we know that we can't create or destroy energy, right? And the energy content of the universe is constant. That is the first law of thermodynamics. We can change forms, but with respect to internal energy, it's already accounting for that. It's always the kinetic and potential energy of the system, right? So if we have a change in internal energy for our system, like there's something, we're losing it, right? How is that going to come? How are we going to get rid of that energy? What are the two ways that we can exchange energy with other things? So one of them was work, right? You can apply a force through a distance. One of them was work. What was the other one? Heat, okay? So this change in internal energy is going to come about via the contribution of two separate things, both the heat of the reaction as well as the work done on or by the reaction, okay? So anytime we're actually going to change internal energy, that's going to come in the form of heat as well as work, okay? All right, so from now on, I'm going to get rid of this distinction of the system. When I'm talking about the system, or anytime you ever see delta E, we're always referring to the system, which for us is always our chemical reaction, okay? So anytime you see delta E, we're implying the system. All right, so now we need to talk about sign conventions, because I always get super confused with respect to sign conventions with delta E and Q and W, okay? So if delta E is negative, again, this is delta E of our system. If delta E is negative, what's happening to the internal energy of our system? We are losing internal energy, okay? So if we have a delta E that is negative, that means that our system is losing energy, okay? A delta E that is positive means that we are gaining energy by the system. The system is taking in energy from the surroundings, okay? How does that translate in terms of Q and W? So if Q has a positive value, it means that heat is being absorbed by the system, okay? So Q is positive, the system is absorbing heat, it's gaining heat. If Q is negative, though, on the other hand, that tells us that the system is losing heat to the surroundings. Okay, so positive value of Q, we're getting in heat, we're absorbing heat. Negative value for Q, we're losing heat. Okay, the other one is work, and work is always confusing for me because we don't do work for the most part in chemistry. So a positive value for work means that work is done on the system. So a positive value for W means that something else is doing work on the system, whereas a negative value for W means that work is being done by the system. Okay, so work is actually doing stuff to the surroundings. Okay, so sign conventions, the definition, how we're actually going to change internal energy, it's always going to come in the form of heat and work. Now, internal energy was a state function, right? We don't care about how we get to our final state. All we care about is the values of the final and the initial state. What do you think is going to happen with respect to Q and W, heat and work? Do you think they're going to be state functions? So just to kind of illustrate this, we're going to go back to our nice little billiard table analogy, okay? So let's imagine that we have a beautiful little pool table. So we've got our little pool table, and let's just zoom in on these guys. And we've got our little white ball here. It's zooming across the pool table to our little purple ball, which is stationary, okay? Our little white ball initially has about 5 joules worth of internal energy, okay? Now, let's imagine that this pool table is super smooth. So nice, flat surface, super smooth, okay? As this guy slides across the table, what's it going to encounter with respect to the surface of the table? Friction, right? And how is that friction going to manifest itself? What are we going to be losing with respect to energy in terms of friction? Heat, right? So we rub our hands together, it gets really hot, that's due to friction. So if this is a nice smooth table, it's going to lose very little of that energy in the form of heat, right? So when it gets to the other ball that's stationary and it collides with it, it's going to transfer most of that energy in the form of work, right? So let's say we'll use about 0.5 joules worth of heat, and then in the collision, we will lose 4.5 joules worth of work. Delta E is 5 joules, which is what it had to begin with, okay? Now let's compare that to what happens if we had the same ball, same 5 joules worth of energy, but now it's on a super rough surface, okay? So as this ball slides across the surface of the pool table, is it going to lose more energy in the form of heat or less? More, right? Because there's more friction, okay? So now, in this example, we end up losing 3 joules worth of work, or worth of heat, due to friction of the table. And so when it gets to the purple ball, it only has 2 joules left to actually transfer in the form of work, okay? So, did it depend on the type of pool table that we use, the amount that we are going to lose in the form of heat and the amount that we are going to lose in the form of work? So in the smooth table, we didn't lose very much in the form of heat. All of it transferred in the form of work. On the rough table, we lost a lot in the form of heat. Not very much was transferred in the form of work. So do those values of Q and W differ depending on the path that we took or depending on the type of table that we were using? Yes, okay. So the moral of this story is the fact that Q and W, heat and work, are not state functions. They actually do depend on the path that we take to get to whatever we're trying to do. Delta E, though, the sum of the two, is a state function, all right? Okay, so let's try one of these, I think, if I'm correct in my organization. Yes, okay. So let's try a problem. We have this beautiful little piston. So this is a piston head, I guess. I don't know much about cars or anything like that. And so we have this piston, and we are warming it via an external flame, okay? It's going to expand, and it's going to do work on its surroundings. If this piston absorbs 559 joules of heat, and it does 488 joules of work, what is the value of delta E for this system? Okay, so think about that. It's on Socrative. And plug in your answer when you're done. Right, so go and get your answers in. Most of you have. With a lot of these, I don't know if this is true for all of them, but I do want you to put the sign in. I know it's implied if it's positive, but just if you want the happy green, then put the sign in. Okay, so we'll go and finish that. Most of you guys got this correct. Again, though, you just didn't get correct on the soccative. All this really has to do with is the sign conventions, right? Making sure that you have these guys straight in your mind. So we have our system here, our piston, and we know that the heat is 559 joules, right? But what is the sign for this? If it absorbs, our system absorbs heat, what is going to be the sign for Q? Positive value. For W, we know that the work done is 488 joules, but it does the work. So what is going to be the sign for W? Negative. And so for delta E here, it's just Q plus W. This is 559 minus 488, which gives us a positive 71 joules. Okay, good. All right, so then next, I've got a couple of different energy exchanges where we have this delta H. I want you to identify whether this is heat or work, and then I want to know what the sign is for each of these exchanges relative to the system. Okay? Oh, no, control. Oh, no. 4.1. Okay. Hold on. Okay, that's better. Okay, so go ahead and get your answers in if you haven't yet. Okay, so let's talk about these guys. All right, so first thing it asks you is whether or not the energy exchange was heat or work, right? So for the first one, we have an ice cube melting. Is this heat or work? So the exchange happens in the form of heat. And now if ice cube is our system, what is going to be the sign of this exchange? So it's cooling the surrounding beverage, ice cube melts. So is it absorbing heat? Is the ice cube absorbing heat, or is it releasing heat? Absorbing, right? So if it's absorbing heat, the sign here is positive. Okay, what about a metal cylinder? Is this heat or work?
Work.
So this guy is work, right? We push something, force through a distance. If the cylinder is our system, then is work being done on it, or is it doing work? The cylinder is doing work or being done on it, right? So if work is being done on our cylinder, what is the sign? Positive. And the last one, steam condensing on skin. So is this heat or work? Heat again. Now what is the sign for this guy? If the steam is our system, this is a negative sign, right? So it is essentially losing heat, right? Where is that heat going to, and how can you tell? Your skin, the surroundings, which get burnt, right? So good indicator of what's happening with respect to positive or negative in heat exchanges is looking at the temperature or what's happening with respect to the surroundings. So surroundings are gaining heat. It has to be coming from our system, which is losing heat, negative. Okay, so moving forward, we're briefly going to talk about the concept of work here in chemical reactions and how we can calculate that. I will never have you calculate work in a chemical reaction, though, so just note that. I just want to show it to you so I can show you how we get rid of it long term. For most chemical reactions, we actually don't do very much work. Okay, so most chemical reactions, any type of energy exchange is going to come in the form of heat. The only type of work that you could possibly see in a chemical reaction is going to be what we call pressure volume work. Okay, so we're going to have the expansion of a volume against an external pressure. Okay, so for example, let's say that we have a reaction given here. We have zinc in the presence of protons, zinc in the presence of H+ ions forming hydrogen gas. Okay, and this is a nice sealed system. So as we produce these hydrogen gas molecules, they're going to essentially escape the liquid and they're going to go into the volume of the flask above it. These guys are going to continue on up into the neck of this flask until they reach this little type of piston apparatus. Okay, so as we begin to increase more and more gas molecules, what's that going to do with respect to the volume of this little piston apparatus? It's going to expand it, right? And so this is what we mean by expansion against an external pressure. Okay, so any type of work that we look at with respect to chemical reactions is usually going to come in the form of some sort of expansion of a volume due to the presence or production of a gas. Okay, so knowing that, how are we actually going to be able to quantify that? So if we are expanding against some sort of external pressure, what is going to be the sign of delta V? Right, so delta V initial, let's imagine, was something like this. We're producing gas molecules, so the volume is going to expand. So this is of our volume initial. If we see expansion, an increase in volume, this is our volume final. What would be the sign of delta V here? The big volume that we've made versus a small volume that we had before. So we would get a positive value for this delta V. Okay? And so if we wanted to define work in terms of pressure times change in volume, what's the problem if we have a positive value for change in V? This reaction right now is doing work on the surroundings, right? And if work is being done on the surroundings, what has to be the sign for W? Negative, right? But if we're measuring this by looking at an expansion of a volume, that expansion of a volume is always going to be positive. And so because of that, we have to put the negative in front to account for the fact that work from our reaction is being done on the surroundings, okay? So just note that in chemical reactions, the only way we measure it is the expansion of volume against an external pressure, and we calculate it through this little equation. We put the negative in front because, again, our sign convention is that work being done on the surroundings is negative. Okay, so again, I introduce work. The only reason I ever do this is because we're very quickly going to get rid of it. I'm going to show you exactly how. All right, so internal energy was sum of kinetic and potential energies. Okay, we're going to move forward now, and we're going to introduce a concept called enthalpy. Okay, so enthalpy is also a thermodynamic function, and it is technically defined as the sum of internal energy plus pressure times volume. Okay, so the technical definition of enthalpy is internal energy plus pressure times volume. Has anyone heard of enthalpy before? Where do you hear this usually? Chemistry, obviously, but do you hear about it in biology as well? Yes, so we talk about enthalpy quite a bit. There's a reason for that. Okay, so because enthalpy is the sum of internal energy plus pressure times volume, we can also define change in internal energy as the sum of the, or change in enthalpy, pardon me, as the sum of the change in internal energy plus pressure times change in volume, okay? So internal energy was a state function. Enthalpy is also going to be a state function, and this is going to become important later on. All right, so now that we have our little change in enthalpy as the sum of these two things, just as a reminder, this change in internal energy we know is heat plus work. Okay, so I'm going to take this guy and I'm going to plug it into my little expression for enthalpy. So I have change in enthalpy is equal to Q plus W plus pressure times change in volume. And now we've also know what W equals. So W equals this minus pressure times change in volume. So if I plug this guy in, I get a minus P delta V plus a P delta V is equal to enthalpy. Okay? Those guys are going to get rid of each other. Those pressure times change in volumes are going to go away, and what we're left with is enthalpy is equal to the heat of a reaction, and this is most important, at constant pressure. Okay, so enthalpy is great. We don't even have to consider work. It's gone, right? Enthalpy, all it is just the heat of a reaction at constant pressure, whether it's absorbed or released. Okay? All right, so conceptually, enthalpy and internal energy are very similar, right? So enthalpy is just the heat of a reaction. So enthalpy is just Q at constant pressure. What is delta E again? How do we calculate that? Delta E was heat as well as what? Work, right? And I've already told you that for the majority of chemical reactions, they do very little work. Okay, so for the most part, for most reactions, delta E and delta H are going to be nearly identical. Okay, to kind of illustrate that, I'm going to do an example. So let's say that we have a butane lighter, and we burn about a mole of butane in our butane lighter. Okay, in the process, we release 2,658 kilojoules of heat, and we also do 3 kilojoules of work, right? So for this reaction, what is delta H? Delta H, what is the change in enthalpy for this reaction? We know that this is going to be heat, right? Heat at constant pressure. How much heat is released in this reaction? 2,658 kilojoules. And what is going to be the sign for delta H if we were releasing, or the sign for Q even? If we're releasing, this is going to be a negative, right? What about delta E? Delta E is Q plus W, right? So we already know what Q is, minus 2,658. What is W? 3, right? So 3 tiny little kilojoules. And what is the sign for W here? It's doing work, so is it positive or negative? Negative. Okay, so delta H was this minus 2,658 kilojoules. Delta E is minus 2,661 kilojoules. Is there that much of a difference between delta H and delta E in this reaction? No. Okay, so this again is why these guys are very similar. Moving forward, though, we're only going to be dealing with enthalpy changes. We're going to get rid of internal energy entirely because, again, there is not much work components with respect to chemical reactions. Okay, so enthalpy. Great, enthalpy. Moving forward. Heat at constant pressure. So now we're going to define two different terms relative to what the sign of delta H is in a chemical reaction. So if delta H is negative, then heat is being released by the reaction or by the system, right? Again, the surroundings are absorbing that heat, and so we're going to call this an exothermic reaction, right? So delta H is negative, and this is what we call an exothermic reaction. A good example of that would be burning things, right? If the burning of something is our system, what's happening to the temperature of the surroundings? Why do we burn things in the first place? To heat up things, right? So the surroundings are gaining heat. That has to be coming from our system. So our system losing heat, losing it to the surroundings. This is an exothermic reaction. On the other hand, if delta H is positive, that means that the system is taking in heat from the surroundings are losing it, then this is what we call an endothermic reaction. Again, a nice little chemical cold pack is a good example of an endothermic reaction. There is a reaction taking place in this cold pack that is taking in heat from the surroundings. How does that manifest itself with respect to the temperature of the surroundings? What is a cold pack supposed to do? It's supposed to do what? Feel cold, right? So it's cold because it's taking in heat from the surroundings. That's how it manifests itself, that it is an endothermic reaction. Okay, so let's try to apply these new little terms that we have, endothermic versus exothermic. So I have a couple of different processes, and I want to know whether or not they are endothermic or whether or not they are exothermic. Nope. Three. Okay, so we'll go over these. Most of you guys get the last two, but the first one struggled, so at least most people struggled with. So for A, we have sweat evaporating from skin. Sweat is our system here. So sweat is the system. The skin is the surroundings, right? So what happens to the temperature of our surroundings when we sweat? What's the purpose of sweating? To cool us down, right? So the temperature of our skin, which is the surroundings, cools down. It has to be losing heat. Where is that going? To the process of evaporation, right? To sweat actually evaporating. So this guy, because of that, is an endothermic process. The skin cools. It has to be absorbing into the system, okay? What about water freezing in a freezer? Water freezing is the system. This is endothermic versus exothermic. So think about what happens to the temperature of our water. Okay, so the temperature of our water, so it goes from, like, let's say room temperature. When we put it into the freezer, what happens to its temperature? It decreases, right? So if its temperature decreases, we're using that as a proxy for what happens to the heat. It has to be losing heat, right? So water freezing in a freezer, it's losing heat to the surroundings. So this guy is exothermic. What about wood burning in a fire? This is probably the easiest one because I've already mentioned it. So what happens to the temperature of the surroundings when we burn wood? They increase. So again, we have this beautiful little exothermic reaction. So endothermic, exothermic, exothermic. Awesome. So moving forward, we're going to start talking about all of the various things that we can do with our little enthalpy values now. Okay? All right, so we are going to stop calling this the enthalpy of the system, and instead we're going to start referring to our enthalpy values as the enthalpy of reaction, or also the heat of the reaction. So these guys are both synonymous with respect to one another. Another little important trait with respect to enthalpy is that it is an extensive property, so extensive, all right? What is extensive property, what does that mean? It depends on the amount of substance that is actually present in the system, right? So if we have 1 log and we burn it, that's going to release so much heat. If we have 10 logs, are we going to release the exact same amount of heat as if we had only 1? No, right? So the amount of heat, the amount of enthalpy that we're actually going to release in a reaction depends on how much stuff is initially there, okay? So by convention, when we write these enthalpies of reaction or heats of reaction, we write them with reference to the balanced chemical equation. Okay, so for example, if I'm dealing with the combustion of propane, and I write that the enthalpy for this reaction is minus 2,044 kilojoules, what that's referring to is that if I burn 1 mole of this, I'm going to get 2,044 kilojoules. If I burn 5 moles of this, I'm going to get 2,044 kilojoules. Okay, so we're going to be able to utilize these guys in a nice little stoichiometric relationship to know how much energy we're actually going to generate given how much starting material we have. Okay, so these are always written with respect to the balanced chemical equation. So how are we actually going to do this? So let's say that we have a certain amount of propane, right? Let's say we have like thousands of grams of propane. And I want to know, well, how much energy am I going to release given this amount of propane? Again, those enthalpies were written with respect to moles in the balanced chemical equation. So if, let's say I had, just off topic, whatever head I have, we have 13.2 kilograms of propane. And I want to know how many kilojoules of energy I'm going to release in this process. How do you think I'm going to go about that? So I have grams, but again, these little reactions, this little stoichiometry is written in terms of moles. So my first step is probably going to be converting grams to moles. Then what do you think I'm going to do? If I want to know, okay, I've got this many moles of things, I'm then going to need the stoichiometry of the reaction to convert from moles of stuff to joules of stuff or kilojoules of stuff given the enthalpy or whatever I'm given for the heat of the reaction. Okay? So, amazingly, this just came off the top of my head. Let's actually move through a problem just like this. So let's say we have a propane tank in the backyard, and it is filled with propane. Okay? And we are going to barbecue a bunch of stuff. right? We're essentially just going to completely combust the entire propane tank, right? So that propane tank initially had 13.2 kilograms of propane in it. When we completely combust it, how much energy are we going to release in this process, okay? So let's go ahead, we'll walk through this, and then I will give you an example or problem where you actually apply this. All right, so 13.2 kilograms of propane. I want to know, long term, how much energy I release in the complete combustion of all of this propane. So my first step here is going to be converting from grams to moles. But the problem with this little thing here is that we're in kilograms, right? So what is my conversion between kilograms and grams? So for every 1 kilogram, how many grams do I get? 1,000 grams. So my first step is converting to grams. So I'm going to multiply by 1,000. That gives me 13,200 grams of this pretty little beautiful propane, C3H8. Okay, so now I want to convert my grams of propane to moles of propane so that I can utilize the relationships that are inherent in the balanced chemical equation. How am I going to do that? I'm going to Google what? Not how much energy is released in this reaction, but instead the molar mass of propane, right? So the molar mass of propane, let's do my little arrow here, is 44.09 grams for every mole. So now I'm going to utilize that to convert to moles of propane. I'm going to take my mass, I'm going to divide by the molar mass for every 1 mole, and that's going to give me moles of propane. That ends up being 299.4 moles of C3H8. So now what is my last little final step? I want to know, this is how many moles of propane I have, how much energy do I release in this process? So now what is the relationship between my enthalpy of reaction and how many propane I have in this reaction? So we go back to the balanced chemical equation. For every one of these, I get 2,044 kilojoules of energy. So now I have 299 of them, right? So I'm going to utilize that stoichiometric conversion. For every 1 mole of C3H8, I get a minus 2,044 kilojoules. So I multiply that, and I end up getting a very large number, lots of energy released. This ends up being minus 6.12 times 10 to the 5th kilojoules worth of energy. So much excitement. All right, so note that that was easy because it was a 1 to 2,000 conversion, right? But if the stoichiometry is different, you have to account for that in this step, right? It's written for the balanced chemical equation. So let's go ahead and try one. Different reaction. We've got ammonia reacting with oxygen. And again, I give you the heat of reaction to the right. I want to know how much heat is associated with 155 grams of ammonia. Okay, so go ahead and get your answer in if you haven't. 3, 4, 5, 6, 7, 8. It's probably more like it. Okay, so what was the correct answer here? I gave you options, wasn't it? Multiple choice. Something like C. And what was C? It was like times 10 to the third kilojoules, something like that. Okay, good. All right, so how would we go about getting that? What was my first step in doing this? You had a mass of ammonia, NH3. And so my first step in answering this question was what? Conversion to moles, right? And I did that by dividing by the molar mass of ammonium, which was 17. That gave me the number of moles of ammonia, which was like 9.10. Now I want to convert to heat or enthalpy, right? But what's the important little conversion here? What is my relationship between the number of ammonias and the amount of heat I get? It's 4 to the enthalpy value, right? So for every 4 moles of NH3, I get 906 kilojoules, or minus 906 kilojoules. So we're going to take our number of moles of ammonia, divide by 4, multiply by the enthalpy of reaction, which gives us this minus 2.06 times 10 to the third kilojoules, okay? Just make sure to note the stoichiometry is important here. All right, so moving forward, great. We're knocking things down. We're getting to other topics. All right, so how do we actually measure these enthalpy values? What little procedure or technique in the lab are we going to utilize to actually get at delta H? So, one more time, delta H is the heat of reaction. Okay, so what we're going to utilize to be able to measure these heats of reaction is something called calorimetry, right? What is the idea and what is the purpose behind calorimetry? So we're wanting to measure these delta H's for our reactions. And kind of the overarching idea behind calorimetry is we're going to have a reaction and it's going to be taking place in some sort of solution. Okay, so for all of the types of calorimetry we're going to use, our surroundings are going to be whatever solution our reaction is lying in, okay? So our reaction is taking place, right? It's exchanging heat with its surroundings, which is the solution. How do you think we can measure how much heat exchanges with the surrounding? Or what little guide or little instrument do we have to kind of measure this idea behind heat? Thermometers, right? So we get this pretty little thermometer, and what we're going to do is we're going to measure the change in temperature of the surroundings of the solution, okay? So this is going to give us our delta T for the solution. How are we going to relate that to our reaction? So whatever happens to the reaction, what do we know about what happens to the surroundings with respect to it? It's going to be the opposite value, okay? So we're going to utilize our solution or our surroundings as a proxy by which we could determine what happens to our reaction. Okay, so this again is how we measure this guy in terms of a calorimeter. So now we've measured, or we're going to measure this change in temperature, but how does that relate to heat? So what is the proportionality between the amount of heat something gains and the change in temperature that you imagine you will see? Are they going to be inversely proportional or directly proportional? Directly proportional, right? So the more heat that something gains, the larger temperature change that we are going to see, right? So this is a direct proportionality. With respect to chemistry, we can always get rid of these guys, these proportionality signs, and replace them with an equal sign, which is what we want. We want something that we can actually measure and calculate as long as we do what? We include in some sort of constant of proportionality, okay? So this little constant of proportionality that we utilize for what we're going to call the heat equation is called the heat capacity of a system. Okay, so capital C refers to heat capacity. and it is going to be specific and unique for whatever type of solution or whatever type of material we are actually dealing with, okay? So we can measure heat via this nice little equation, or a little ramification of this equation later on. All right, so again, heat capacity is essentially just going to be a measure of the abilities, or the system's ability to absorb heat. Now, there's a problem with heat capacity, as is. Number one, it depends on the system, right? So it is an intensive property. Different types of things are going to have different heat capacities. So these are going to have to be standardized values of things that you look up in some sort of table, okay? Number two, it is also an extensive property, meaning it depends on the type or the amount of stuff that is actually there. So because of that, because we don't always know how much stuff is there, or we don't want to have to calculate that into our heat capacity, we will also define something that is a little bit more important, which is called the specific heat capacity, okay, or specific heat. So now the specific heat capacity is essentially going to be the measure of the energy required to measure 1 gram of substance 1 degree Celsius, okay? So specific heat capacity is going to be energy. So energy required to measure or to raise the temperature of 1 gram of substance 1 degree Celsius. That's what we're going to define as the specific heat capacity. So note that, again, all of these guys are nice little constants. And we can look at this table and look at these specific heats for various different things. So note as we compare these, we have a 1. What does that mean? 1.04 as a specific heat means that we need 1 joule to raise 1 gram of nitrogen 1 degree Celsius. On this table, who has the largest value for specific heat? So if we go over here too, we have others that are a little bit more important. Who has the largest specific heat capacity? Water, right? So water has a very, very, very high specific heat capacity. And that has very important ramifications with respect to the importance of water in life and in biology. So just to give you an idea about what this specific heat capacity or how it manifests itself in real life, I want you to consider the differences in climates between a city like Sacramento versus San Francisco. Okay? So San Francisco, where is that at? Just geography. It's in California. Most importantly, though, it is on the coast of California, right? It's surrounded by water. So beautiful, right? Now, if we compare San Francisco to Sacramento, where is Sacramento? It's inland. It's also in California. But if you look at their latitudes, they essentially lie at the exact same latitude, right? So they get the exact same amount of sunlight every year and every day. How drastically different are the climates between San Francisco and Sacramento? Very different, right? So Sacramento is essentially just a desert, right? Whereas San Francisco is beautiful and it's like 70 degrees every day, right? How could we explain that? They both get the same amount of sunlight every day, every year. What's the difference between San Francisco versus Sacramento? This guy's landlocked, right? But this guy is surrounded by this beautiful substance that we call water, right? Water has a gigantic heat capacity compared to land. It can absorb lots and lots of heat without changing the temperature that much, okay? So this is a very good example of the implications behind the high heat capacity of water. It absorbs lots of energy, and it doesn't change the temperature of the surroundings very much, okay? Okay, so moving forward, we're going to be utilizing these little guys, these specific heat capacities. And we're probably going to use water quite a bit. All right, so how are we actually going to calculate heat now that we know our specific heat capacity? So this is what introduces us to our heat equation. So heat is going to be equal to the mass of whatever we are dealing with times the specific heat capacity times the change in temperature. So this is how we are going to measure Q. And then once we know Q, we're going to be able to figure out what delta H is experimentally. Okay? So again, this is our heat equation, mass times specific heat times change in temperature. Okay, so now let's get into how you guys will actually utilize that when you're experimenting and trying to determine delta H. So the type of calorimetry that we utilize to determine enthalpies is something called coffee cup calorimetry. Okay? The idea behind this is that our calorimetry, or our measure of these changes in enthalpies, are going to be done in a coffee cup. Right? Why do you think we use a coffee cup? It's insulating, right? So ideally what we want is this nice isolated system that can exchange heat and it can exchange matter with the surroundings. The coffee cup is going to be a perfect situation to do that in, okay? Also what's going to happen in the coffee cup is we're going to have a solution in there, right? The solution is going to be what we call our surroundings. Okay, so the solution is our surroundings, and in the solution, we've got our little particles or solutes dissolved. This guy is what is happening with respect to our reaction. So with coffee cup calorimetry, our reaction is taking place in the solution. The solution is the surroundings, though. Okay? We are then going to measure the change in temperature upon whenever this reaction occurs. So we're going to measure a delta T, and that is the delta T with respect to the surroundings. We're then going to take that. We're going to use our little heat equation that we just found to figure out what happens to the heat of the solution, or the heat of the surroundings. With that, we will be able to know what happens to the heat of the reaction, because again, they're just going to be the reverse of one another. And then once we know that, we will be able to calculate the enthalpy of the reaction, knowing the heat of the reaction, and then also knowing this little value N. What is N represented so far? Moles, right? So this is going to be the number of moles of limiting reagent. Damn. Okay, we're getting close. All right, so I'm going to do this real quick, if it's not quick enough as is. All right, so we're going to use coffee cup calorimetry to determine overall these enthalpies of reactions. This is how we're going to get this stuff experimentally. So let's utilize an example to try to illustrate what's going to happen in these types of problems. All right, so we've gone into the lab and we want to determine what the enthalpy of this reaction is, where we have magnesium reacting with HCl, forming magnesium chloride as well as hydrogen gas. Okay, this is the ideal. What we're trying to get is delta H for this reaction. We're going to utilize our little coffee cup calorimeter, right? So we have our little coffee cup, right? We put a little lid on it. It's nice and pretty. And in our little coffee cup calorimeter, we have poured in 100 mils, and I didn't mention this, this is a 0.200 molar HCl solution, okay? So we put in 100 mils of our HCl. We have also measured out a tiny little piece of magnesium. This is our tiny little piece of magnesium, and we're going to throw it into our little solution to initiate the reaction, right? At that point in time, we're going to cap it, and we're going to measure the change in temperature of our solution via our nice little thermometer. So we throw this guy in. What we find, temperature initial for this reaction was 25.6 degrees Celsius, and then the final temperature was 32.8 degrees Celsius. So how are we going to utilize all this amazing data to figure out what delta H is for this reaction? Okay, 3 different equations. Number 1, our heat equation for the solution. Number 2, the relationship between the solution and the reaction. And number 3, enthalpy of reaction is heat of solution divided by number of moles of limiting reagents. We're going to start with number 1 because this is going to tell us everything. So, heat of the solution. What do I need? I need mass, I need specific heat, I need change in temperature. Okay? What do I already know without even thinking about it? Change in temperature, right? We've measured that, so we can calculate. This is final minus initial. And so delta T for this ends up being a 7.2 degrees Celsius. All right, so now, what about mass? Mass of my solution. What do I know about the volume of my solution right now? It's 100 mils, right? And with respect to this type of solution, what is this? What is the liquid in our little coffee cup calorimeter? It's HCl, right? So what is the majority of HCl? It's 0.2 molar, right? HCl is HCl in what? Water, right? So our solution approximately is water, okay? And we're just going to imagine that it is water for the most part, okay? So what little parameter of water will essentially allow us to determine the mass given the volume of our solution? Density, right? So the density of water is 1 gram per mil. If I have 100 mils, what is my mass? 100 grams. So my mass right now is 100 grams of water because of the density, okay? All right, so I plug that into my little heat equation, 100 grams for my M. This is going to be times, what is the specific heat of this solution? Again, what is it the majority of? What is the majority of my solution? It's water, right? So I'm just going to use the specific heat of water, 8.4, and then times delta T, which we just calculated, was 7.2 degrees Celsius. So the heat of the solution here ends up being a positive value, positive 3012 joules. All right, so if that's my solution, what's my reaction value? So heat of reaction is the negative of whatever happened to the solution, right? Because the solution gained it, so the reaction had to have lost it. So Q of reaction is minus 312 joules. That's 2 of them. Now what do we need? Delta H, this is what we're going for this entire time. This was Q over N. We have Q, right? We just calculated it. This is minus 3012 joules. N, though, what is N? N is the number of moles of limiting reagent. What a hassle, right? So what are my 2 reagents that I have to consider? We've got magnesium, we've got HCl, right? I had a mass of magnesium. How would I convert that to moles? Divided by the molar mass of magnesium, we'd look that up on the periodic table. What we would find is we would have 0.0065 moles of magnesium. What about HCl? HCl, I had a volume and I had a molarity. How would I get moles of HCl? Times, so molarity times my volume is going to give me my moles of HCl. So this is 0.02 moles. Who is limiting? So you can look at the stoichiometry, but we'll just cut to the chase. This guy is our, that's great. This guy is our limiting reagent. So we're going to take those guys down here at the bottom. 0.0065 moles. That's going to give me a fairly large number. So we get minus 463,385. Right now we're in joules. But what else is part of this little unit? When I calculated enthalpy, I had Q divided by what? Moles. So this is joules per mole as a unit. Big numbers, don't like to write them. So what's a better conversion to put this in? Kilojoules, right? So if we wanted to write this in kilojoules, we would move the decimal 3 places to the left, and we would be left with minus 463 kilojoules per mole. Okay, that's it. We'll start with a problem just like this on Tuesday. But now you guys should be able to do lots of your homework, so that's great. Okay, so with our solution, what did we put in? What was the total volume of our solution? We put in 50 mils of one reactant, and then we put in 50 mils of another reactant. That gave us a total volume of 100 milliliters. Okay, now we're going to assume what about the solution? That it is primarily composed of water, right? And so we're going to utilize the density of water to convert our volume to mass, because the M here is mass of solution, okay? So if the density of water is 1 gram per mil, and we have 100 milliliters, what is the mass of that 100 mils of water? 100 grams. Okay, so that's how we determine the mass of the solution. Now again, we've already assumed that the solution is primarily water. Okay, so we're going to use the specific heat of water as our specific heat capacity here. So this is going to be 100 grams times the specific heat of water, which is 4.184 joules per gram degrees Celsius. And then what is my last little bit here? What is delta T? So delta T is final temperature minus initial temperature. That gives us a difference of 0.81 degrees Celsius, right? And it's positive because the temperature is increasing. So we'll go ahead and plug that in. When we calculate our heat of solution, we get a value. So we'll go down here. Heat of solution is equal to a positive 338.1 joules, okay? 0.9, pardon me. If that's what happens to our solution, then what do we know happened to the reaction? Because heat of reaction is what comparatively to the solution? Just the negative, just the opposite of whatever happened to the solution. The reaction is our system, the solution is the surroundings. So heat of the reaction is just going to essentially be the negative of what we calculated for the solution, 0.9 joules. So we'll go ahead and put this guy up here, minus 338.9 joules. And now for the enthalpy, delta H for the reaction, this is heat of reaction over N. Okay, and N was the number of moles of the limiting reagent. And so just conceptually to think about that, what happens as we have a reaction progress with the limiting reagent, right? What happens when we run out of limiting reagent? The reaction stops, right? And so once we run out of limiting reagent, then we're not going to produce any more heat. And so that's why we define enthalpy in terms of N, which is the number of moles of limiting reagent. For this problem, how would I figure out what N is? I have two reactants, right? I have silver nitrate, I have HCl. I have a volume, and what else do I know about these two reactants? Their concentrations, right? So how would I determine how many moles I put in for both of them? So concentration molarity is moles divided by liters of solution. For both of them, I would take their concentration, 0.1 molar, and I would multiply it by the volume in liters. So for both of them, we end up with 0.005 moles, okay? So if both of them have 0.005 moles, then who's the limiting reagent? Both of them, right? We're going to run out of both of them at the exact same time, okay? So the 0.005 is what we use in our enthalpy equation over here, right? So now we have our heat, minus 338.9, divided by the number of moles of limiting reagent. It's 0.005 moles. And we're going to end up with a fairly large number for enthalpy, which is equal to minus 677, who cares, 80. This is in joules per mole. Again, converting this to kilojoules, we're just going to move the decimal 1, 2, 3 places to the left. So minus 67.8 kilojoules per mole. So 3 different pieces you guys have to be aware of, okay? I can almost guarantee that there will be a coffee cup calorimeter question on the exam. Promise it, because I love it so much and I think it's so important, so why not? Why wouldn't I put it on the exam, right?
It's a hot topic.
Yeah, hot topic these cold days. Okay, are we good here? Okay, all right, so just note that this is how you would actually go about determining these enthalpies of reaction, okay? So if you really wanted to go in, you could go in for every reaction and use coffee cup calorimetry to do that. How big of a hassle do you think that would be long term? pretty big, right? So we're going to be very interested in heats of reaction and enthalpies of reaction, but we don't want to have to go in and do this every single time for every single reaction, okay? So we're going to utilize the fact that enthalpy is a state function. So remember what state functions are. We're also going to be able to utilize the fact that enthalpy is an extensive function, meaning it depends on the amount of stuff present, okay? We're going to utilize those two facts to be able to develop some relationships that are going to allow us to determine the enthalpy of a reaction without actually having to measure it experimentally, okay? Okay, so what are some of those relationships that we're going to develop? So I'm going to go through 3 different relationships, and then I'm actually going to show you how you're going to apply them. The first relationship that has to deal with the enthalpy for a reaction and the overall chemical equation is given here by number 1, okay? This states that if you have a chemical equation and you multiply it by some sort of factor, some sort of number, then if you want the new enthalpy for the new reaction, you're just going to multiply that enthalpy that you know by that factor. So that seems kind of confusing. I'll try to illustrate what I mean. So for example, if we have a reaction, we have A plus 2B going to make C, and we know this enthalpy, so this is known, and then in a different reaction, we essentially just have 2A plus 4B going to make 2C. What is this second reaction compared to the first? What have I done to it? I've multiplied it by 2. Okay, so if we've multiplied an equation by a number, then the enthalpy of that new equation is just going to be the enthalpy of the first one multiplied by that same number. Okay, so if you multiply a reaction by a number, all you have to do is multiply the enthalpy by that same number to get the new enthalpy. Okay, so that's number 1. Number 2, if we have a reaction and we reverse the reaction, right? So if we take a reaction as is, say we have A plus 2B going to C, and we reverse it, all we have to do for the new enthalpy value is change the sign of the original enthalpy, okay? So reverse a reaction, you're just going to put a negative in front of the enthalpy. Okay, so those are fairly easy. The last one is a little bit more complicated, and it kind of encompasses everything that we're going to utilize with respect to these other 2. So the last little relationship is what is called Hess's law. Okay, so what it states is that if you have a reaction that can be expressed as a series of separate steps, okay, the overall enthalpy for that reaction is just going to be the sum of the enthalpies of the separate steps. So this kind of goes back to the fact that enthalpy was a state function. So what is the state function again? What was the big idea? Like we went up the mountain one way, and we found our change in altitude, and then we took a different path. We went up, and we went down, and then we went back up again. But between the 2 paths, did the altitude change differ at all? No, it was the exact same thing, right? It's the exact same thing with enthalpy. It does not matter if we go directly from point A to point B. If we compare that to going from point A to C and then back down, that's going to give us the overall same enthalpy change regardless of which path we take, okay? And this is what Hess's law is supposed to be illustrating. Okay, so one thing to note about Hess's law, when we sum reactions, right? So let's say I have reaction 1 and I'm summing it with reaction 2, so I'm adding them together. Anything that shows up as a product as well as a reactant in the exact same number, exact same phase, can cancel, okay? So if I sum these 2 reactions, then I would be left with A plus 2B going to make 2D. And again, with Hess's law, what it's stating is that the overall enthalpy for this reaction is just the sum of the 2 enthalpies of the reactions that I essentially added together, okay? Okay, so now let's utilize this in a real-life problem to show what I mean by how we're going to utilize these relationships. Okay, so let's say that we have a reaction. We have this reaction right here, and we want to determine what the enthalpy for this reaction is. We don't want to have to go into the lab to find that out, okay? What we do know, though, is the enthalpies and the reactions, the equations for these 3 separate reactions, okay? So the goal behind all of these types of Hess's law problems is we're going to take these 3 reactions, we're going to manipulate them using those relationships that I just showed you to get the enthalpy for this overall reaction, Okay, so this is the goal. All right. Now, how are we actually going to go about doing this? So I'm going to change the slide because I have more room on the next slide with the exact same information. Okay, lied about that. Oh, there it is. Okay, good. All right. All right, okay. So, again, this is our overall reaction. We want to determine the enthalpy for this. We are going to utilize 1, 2, and 3 and their known enthalpy values to determine that. So how are we going to do that? With respect to Hess's law, what I always like to do is start with the first reactant, okay? And so in my unknown reaction, my first reactant is carbon, okay? I look at carbon, I look at where it's at, and I also look at the number in front of it. And then I go down to my 3 known reactions, and I figure out where carbon is located, or whatever that first reactant is, where it's located, right? So in these 3 different reactions listed down below, where is carbon at? Is it in 1, 2, or 3? So carbon, as a solid, by itself, is listed in equation number 1, right? And so I find it, and then I figure out, does it have the exact same number in front of it as my first one up here? So is carbon listed in the exact same way in this reaction number 1 as it is in the unknown reaction? Yes, okay? So because of that, I'm going to take this unknown reaction, and I'm going to take, or this known, pardon me, and I'm going to take it as is. So no changes to it. I'm going to go ahead and rewrite it. Carbon solid plus oxygen is going to go to form CO2 gas, okay? And I'm also going to recopy the enthalpy value for this reaction. So this is delta H1 is equal to minus 393.5 kilojoules. All right, so now check on that guy. Who is my next reactant? Because that's what I move into in my unknown reaction. Water, right? So I take water, and I go down to my list of 3 reactions below, and I figure out where is water located. So where is water in these 3 reactions? It's in the third one, right? So we have water right here. What's the problem with it, though? It's a product in the known reaction, and it has a 2 in front of it, okay? So that's fine. If I want to get this water to look like it does up here, what do I need to do to this third reaction? I need to flip it, so I need to reverse it. And then I also need to multiply it by a factor. What is that factor if I want a 1 in front of something that has a 2 in front of it? 1/2, okay? So I'm going to reverse and multiply by 1/2. So I'm going to do that to the entire equation. That's going to give me H2O gas goes to make 1H2 and then a 1/2 O2. So that's fine, I can do that. But if I do that to my equation, what do I also have to do to the corresponding enthalpy value? I have to do the exact same thing, right? So I'm going to take this enthalpy, and I'm going to change the sign. I'll put a negative in front because we reversed it, and I'm going to multiply it by the 1/2 as well. So this is minus 483.6. So my new enthalpy for this guy is a positive, what was it, 241? 241. 241.8. Okay, so that's carbon and that's water. What is my next product, or what is my next thing in my overall reaction? CO, okay? So now I'm going to go below in my 3 equations. I'm going to figure out where CO is located, right? So which equation has CO in it? Number 2, right? So again, what's the problem with CO in the second reaction? It's got a 2 in front of it. I need it to have a 1 in front of it. And also, it's a reactant, and I need it to be a product, okay? So what am I going to do to this second reaction to get CO to look exactly like it is in the unknown? I'm going to reverse it again. So I'm going to take this guy and reverse, and I'm also going to multiply it by 1/2, okay? So when I do that, I'm going to get a CO2 going to make a CO, and then another 1/2 O2, okay? So if I reverse my reaction, I times it by 1/2. I have to do the exact same thing to the enthalpy. This is going to be a minus 1/2 of a 5, or negative which gives me a positive 283 kilojoules. Okay, so now, when you get to like the third reactant or the third product or whatever, however many chemicals you actually have to go in, this is about the time that things are going to start canceling and we're going to get the overall reaction, right? So if I have these guys now and I sum these three equations, there's going to be some things that cancel, right? So for example, we have a CO2, let me highlight it. So we have a CO2 up here as well as a CO2 down here. We have it on the products. On that first one, it's a reactant on the second. So if I sum these, what's going to happen to the CO2? They're going to cancel, right? So we have this guy canceling. That's good. Another thing that we have is an oxygen as a reactant, and then we have a half oxygen and a half oxygen as a product. So what are two half oxygens summed to? An oxygen, right? And so because of that, one oxygen is going to cancel with these guys. And so what are we going to be left with in this overall reaction when we sum everything? We're going to come up with a carbon. We're going to come up with a water. It's going to go to form a hydrogen and a CO. And so was that the goal? Was that the overall reaction that we wanted to determine up here? Yes. Okay. All right. So we have essentially expressed our reaction as a sum of series of steps, right? So if I want the enthalpy for this reaction, for this guy, what do I need to do? I just need to sum the enthalpies for the three steps that I have essentially added together, okay? So for this one, this would be minus 393.5 plus a 241.8 plus a 283. So when we add all of these guys together, the overall enthalpy for this reaction is equal to a positive 131.3. And the units are kilojoules. This was this guy. Okay, all right. So if you're systematic about this, and you start at 1, and then you move to 2, and then you move to 3, by about 3 in, things will cancel, and you will end up with your overall reaction, which is what you're trying to determine. Okay, so let's try that with a problem. Again, I like coffee cup calorimeters. I really like Hess's law too. So it may not be as detailed in the exam, but it will probably be there. Nope, I don't. Okay, so I want to know delta H for this reaction given the three reactions below. Okay, so try to take another moment or two and get your answer in. Okay, so let's go ahead and talk about this one. I know maybe some of you guys aren't done, but we are limited in time. So I think I put in the right answer. I'm not sure. With Socrative, if you had put in the answer C, it was showing up as correct. So we'll see if that is the correct answer. So for this one, we have our unknown equation. We're trying to determine the enthalpy for, and we're going to be utilizing these three known equations, right? So number one, I'm going to start with my first reactant. Of these three reactions down below, where is N2O located? It's in the third reaction, right? What is the problem with it in the third reaction right now? It's got a 2 in front of it, right? But I want it to have a 1 in front of it. So I'm going to take this third reaction, I'm going to multiply it by 1/2 to get N2O with a 1 in front of it. Okay, so I'm going to take that N2O goes to make 1 N2 and a half O2. And so if I do that to the reaction, what do I have to do to the enthalpy value? I also have to multiply it by 1/2. So that's going to give me a minus 81.6 for that reaction. So next we've got NO2. Where is NO2 located? First reaction, right? So first reaction, we have NO2. It's got a 2 in front of it, that's a problem. And it's also a product, right? So what do we need to do to this first reaction to rectify that? So we're going to reverse, and we're also going to multiply by 1/2. So that's going to give us NO2 going to make, I get so confused when I do these. Okay, NO2 going to make an NO and another 1/2 O2. So for the resulting enthalpy change, I'm going to flip the sign of equation number 1 on the enthalpy. I'm also going to multiply by 1/2. So that gives me an enthalpy value for this reaction equal to 56 kilojoules. So correct me if I'm wrong on any of these. I do get confused. And so next, that's 1, that's 2. I usually say, oh, once you get to the third, things are going to become super clear. It's going to just appear out of sky, right? This one's a little bit different. The last reactant, or last product, is NO. I already have an NO in the 2 reactions that I've messed with, right? I have an NO present right now as a product in equation number 2. So how many more NOs do I need to get 3 NOs total? 2 more, right? Who has 2 NOs as a product? Which reaction? Number 2 as is, right? So 2 as is has 2 NOs, which is exactly what I need, okay? So if I take number 2, I've got nitrogen plus oxygen going to make 2 NOs. And again, if I take it as is, I'm just going to take the enthalpy value also as is. So this is a positive 182. So now, if I go about summing things, I've got a nitrogen up here. I've also got a nitrogen down here. I'm going to get rid of those 2. I've got an oxygen, and then I've got 2 1/2s, right? So those are going to cancel. Okay, sorry. Yes, is there a question? Right. So that was the point that I was trying to make. Like, doing the things that I had already done had given me 1 already in my reactions. And so now I just needed 2 more, and those 2 were coming directly from number 2. Does that make sense? So this is a little bit of a trickier one, okay? So then, once I cancel out the oxygens, the nitrogens, I'm left with N2O, NO2, and then 1, 2, and 3 NOs. So we'll go ahead, N2O plus NO2, going to make 3 NOs. So that is the overall reaction that I wanted. And so now, to get the enthalpy for this, I just need to sum the 3 enthalpy values from the series of steps. And when I do that, I get a positive 157.6 kilojoules. So it's like a little puzzle sometimes, just with a bunch of letters that are supposed to represent chemicals. Okay, so which one between this one and coffee cup calorimetry, which one did you prefer more? This one? Okay, all right. So I know this, we build this all up, we're like, look at this, now we have all these reactions, we can combine them and get the enthalpy for what we want. I'm going to show you an even easier method for determining the enthalpy for any reaction that you could possibly want, utilizing a very, very, very similar principle to what we just utilized, okay? But before we can do that, we have to develop a few more definitions. Okay. All right, so a couple more things to talk about. We're going to define something called standard state in chemistry. So we're going to utilize standard state quite a bit. So it would be very beneficial if you became at least aware of it and understood its meaning at this point in time, okay? So the standard state of a chemical is defined as the following, okay? So if you are a gas, your standard state is the pure gas at 1 atmosphere pressure. If you are a solid or a liquid, it is your most stable form, okay? And if you are a solution, you're going to have a concentration of 1 molar. Okay, so this is how we define standard state for chemicals in a chemical reaction. So 1 atmosphere pressure, most stable form for a liquid and a solid, and then if you're a solution, you have a concentration of 1 molar. Okay, so with that, now that we've defined standard state, we are going to define something called the standard enthalpy change, right? So we have been looking at delta H Rxn, and so we're going to define the standard enthalpy change as the enthalpy for a reaction when all of our reactants and products are in their standard state. Okay, so that means if it's a liquid, it's the most stable form. If it's a gas, it has 1 atmosphere pressure, etc. The way we denote that we're at standard state is we put this little 0 up above in the superscript. Okay, so that is telling you that this is the enthalpy value for a reaction when all reactants and products are in their standard form. Okay? And then one more, we will define something called the standard enthalpy of formation. This is given by this delta HF. And this little 0, I tend to call this naught, right? It means 0, but I call this delta HF naught, so enthalpies of formation. What this is defined as the enthalpy of a reaction when you form 1 mole of product from the constituent elements in their standard state. Okay, and again, we're going to spend a little time with this enthalpy of formation for a second, so just note, this is just the enthalpy for a reaction when you form 1 mole of a product from their constituent elements in their standard state. Another important thing to note is that the enthalpies of formation for a pure element is going to be 0. Okay, so we kind of arbitrarily define this, but the idea behind this is, again, enthalpy has to do with energy. And if you have something that is in its pure elemental form, does it require any energy to actually make it? No. Okay, so we define anything that is in its elemental form to have an enthalpy of formation equal to 0 because of that. And again, we're kind of arbitrarily defining that 0 point. Okay, so how are we going to utilize these guys? How are we going to utilize these enthalpies of formation to calculate our enthalpy of reaction? So the next thing we're going to do is we're going to define what a formation reaction is. And so in a formation reaction, we are essentially making 1 mole of product from its constituent elements. Okay? So let's say I wanted to write the formation reaction for CO, gas. Okay? In this formation reaction, I am again going to be forming the thing that I want to write the formation reaction for. Okay? I'm going to be forming it from things in their elemental form, whatever makes it up in its elemental form. So what makes up CO, carbon monoxide? What elements go into it? Carbon, right? So carbon's 1, as well as oxygen. Okay? Now the big rule here is that these guys, the reactants, have to be in their elemental form. So what is the elemental form of carbon? So it's just solid. Most things just have an elemental form of carbon, or like whatever type of metal, non-metal, tend to have an elemental form of just a solid. There is a specific type of solid carbon though, and you don't necessarily have to know this. So carbon, most stable form, and this is where the whole standard state or the standard conditions comes in, is graphite. Does anyone know another type of solid carbon? Diamond, right? So who do you think is more stable, graphite or diamond? Or whose are more of in the world? Graphite. Okay, so this is what we mean by most stable form of a solid. So carbon graphite is the elemental form of carbon. What about oxygen? What is the elemental form of oxygen? O2, right? So oxygen is diatomic, and its elemental form is O2. Now the big thing with formation reactions, we're going to be forming things from their constituent elements, but this has to be balanced, so there is a 1 in front of the thing that we're making, okay? Because, again, these are written to form 1 mole of product. So this is the only time in chemistry that you get to use essentially fractions as stoichiometric coefficients. If I want to balance this, so there is a 1 in front of the CO, what do I need to put in front of the carbon? Just a 1, right? But what do I need to put in front of the oxygen? I need a half of an oxygen here, right? Because again, I only want 1 of these, so I'm going to take a 1/2 of my O2. So formation reactions, you're making 1 mole of product from constituent elements, and you have to balance it so there's a 1 in front of the product, okay? So now, what do we mean by these enthalpies of formations? This is what this is referring to, right? This enthalpy of formation of CO is the value that is essentially made from this formation reaction. And what's great about these enthalpies of formation is that we can go and look them up in a tabulated list in the back of the book, right? So I can look up the enthalpy of formation of CO and find that it has a standard value, and that is equal to minus 110.5, and that's in kilojoules per mole. Okay? All right, so this is the enthalpy for this reaction. It's going to be important. So what's also great is that we don't just have to know the enthalpy of formation of CO, we can look it up for pretty much everything, okay? So if we look at the next slide, I give you just a random assortment of tabulated enthalpies of formation for pretty much anything you could ever want to look up, okay? There's going to be one important thing to note, and it's not actually listed in this table. So the enthalpy of formation, I've already mentioned this, but just to make sure that everyone got it, the enthalpy of formation for anything in its elemental form, what is it equal to? 0. Okay, so you will look up in the back of the book things like O2 or things like carbon solid graphite, and you will find that they have an enthalpy of formation of 0. So if you're ever confused about what is the elemental form of something, it's the thing that has delta HF equal to 0 in your back of tabulated list of values, okay? Okay, so where is this going? What's the point? We're going to go ahead and skip this one really quick just to get to the end of this. So how are we going to utilize these enthalpies of formation? Okay, so this also goes back to Hess's law, as well as the fact that enthalpy is a state function. Okay, we have just defined the enthalpies of formation as the enthalpies when we're taking elements and making compounds, right? What if I wanted to do the reverse? What if I wanted to take a compound and decompose it into its constituent elements? What would that be representative of? If formation is going from elements to make compounds, then what would compounds to elements be? just the negative of the formation reaction, the negative of the enthalpy of formation, right? So let's say that I wanted to take something like methane and combine it with oxygen to form CO2 as well as 2 waters, okay? So if I took my methane and I broke it down into its constituent elements, so that would be carbon as well as hydrogen, how would I determine that value for that reaction specifically? What is this the reverse of? Taking a compound and breaking it down into its constituent elements. This is just the reverse of the formation, or the enthalpy of formation of methane. So if we go back to what we were doing before, if I reverse a reaction, what do I need to do to the sign of my enthalpy? I just need to put a negative in front of it, okay? What about this guy? What about oxygen? If I wanted to decompose it, is there anything I can break it down into? No, it's already in its constituent or its elemental form, right? So this guy is just going to come with us, all right? So for this part, breaking things down, I'm going to look at the enthalpy or the negative enthalpies of formation of whatever reactants I have. Now, if I want to build things up, all right, if I want to take things in their elemental form and make compounds with them, what is that representative of? The enthalpies of formation, right? So if I wanted to form CO2, I could do so from my carbon as well as one of my oxygens. So this would be representative of delta HF of CO2. Of course, we can't see that anymore. What about water? If I wanted to make water, what would that be indicative of? From its constituent elements. The enthalpy of formation of H2O. Except now there's this big thing in front of this. When we wrote these enthalpies of formation, we wrote them in terms of 1 mole of product, right? If I have a 2 in front of oxygen, that's okay. If I multiply a reaction by 2, what do I need to do to the enthalpy? Also multiply it by 2. So this would be 2 times the enthalpy of formation of water, okay? So what does this kind of come down to? All of these guys, this reaction, if we want the enthalpy for this overall reaction at standard state, is essentially just going to be the sum of the enthalpies of formation of our products minus, because there's a negative in front because we're reversing it, the enthalpies of formation of our reactants. And so now with all of these tabulated values that we'll have in the back of the book, to calculate the enthalpy for any reaction, all we need to do is look up the enthalpies of formation of our products, and we need to subtract the enthalpies of formation of our reactants. The only thing that's left to do is we have to include that multiplication, right? So if there is a 2 in front of water, then I have to multiply that enthalpy of formation by that number, okay? So what does this overall kind of condense down into? Condenses down into this beautiful little equation, which is given as follows, okay? So the enthalpy of formation, or enthalpy for any reaction, is just going to be the sum of the enthalpies of formation of products multiplied by their stoichiometric coefficients minus the enthalpy of formation of reactants multiplied by their stoichiometric coefficients. All of that works up into this nice little equation. I like to explain where it comes from, though, so it's not that we just throw something at you and you don't necessarily understand where it ever even came from to begin with. All right, so let's utilize this. Let's do a problem. We want to calculate the enthalpy for a reaction given these tabulated values of formation constants. So let's do that. People are scribbling still, scribbling. Okay. Okay. So we have a reaction. Ammonia reacts with oxygen to form NO and H2O. We want to calculate delta HF, delta H, pardon me, not F, the enthalpy of reaction at standard state for this reaction utilizing these delta HF values that we've looked up in the back of the book. Okay? How are we going to do that? So we'll take our little equation as equal to the sum of the enthalpies of formation of products multiplied by their stoichiometric coefficients minus the sum of the enthalpies of formation of reactants multiplied by their stoichiometric coefficients. I'm going to start with the products, and I'd like to employ brackets here. So my first product is NO. How many of them are there? 4. So that is my stoichiometric coefficient for 4. That's taking into account that it is extensive. 4 times my enthalpy of formation for NO, so this is a positive 91.3. And note that the units are kilojoules per mole. That's given up here. First product, down. We're summing this with the second product, right? It's the sum of the enthalpies of formation of products. How many of my second product do I have? 6 times the enthalpy of formation of water. And note that water is in its gaseous state. So this is a minus 241.8. Products are done. I'm going to subtract from that my reactants. Same exact thing. First reactant is NH3. There are 4 of them. NH3 has a value of minus 45.9. And I'm going to add to that the same thing for oxygen, right? What's the difference with respect to oxygen now? So there are 5 of them, but what is the value for the enthalpy of formation of oxygen, O2 gas? 0, right? Why is that? Because it's in its elemental form, okay? Anything in its elemental form has an enthalpy of formation equal to 0. You should know that and memorize that or do something with it. Okay, so now values are plugged in. What is the rest of this? It's just adding, subtracting, multiplying, etc. So delta H for this reaction at standard state is equal to a minus 902 kilojoules. The only other thing I want to note is this unit, kilojoules per mole. When we multiply this stoichiometric coefficient in, it cancels the moles. So the last thing that we're left with, the moles all cancel, and we're left in units of kilojoules because it cancels, okay? Also note that this negative goes to everything in the reactants. It's not just that first thing. So we have plenty of time for you guys to utilize this on your own and do a problem. So this last little question I have is doing this exact thing. I'm going to provide you the enthalpies of formation. They're not written on the slide. But all I want you to do is calculate delta H for this reaction. Okay, so I had presented this problem at the very end of class on Tuesday when we finished chapter 5, and we didn't actually go over the answer, so I was going to go ahead and just record over that original part and go ahead and go through the actual answer for this problem, right? So now that we have developed this idea behind enthalpies of formation, we can calculate the enthalpy of any reaction given these standard tabulated values of enthalpy of formation, right? So if we have a reaction and we want to know what the overall enthalpy for this reaction is, and note that this is at standard state, right? So standard state means that all of the reactants and products are in their standard state. So for gas, that's 1 atmosphere. If we were dealing with a solution, it'd have a concentration of 1 molar. And again, that is denoted by this little 0 in the superscript. Okay, so that doesn't necessarily matter on how to calculate this guy. So we had developed this little equation that stated that the
enthalpy of reaction is equal to the sum of the enthalpies of formation of our products multiplied by their stoichiometric coefficients minus the sum of the enthalpies of formation of our reactants multiplied by their stoichiometric coefficients. And so then I had also given you these various enthalpies of formation for all of our reactants and products. So I had given you over on a little table, I had listed chemical or substance, or whatever you want to call it, and this was C2H6, and we listed that as a gas. It had an enthalpy of formation of minus 84.68. And again, the units here are kilojoules per mole. Then we had next oxygen. So oxygen is in the standard state. It has an enthalpy of formation of 0. And again, that's something that you guys should kind of be aware of. And then CO2, gas, enthalpy of formation. This is really pissing me off. Enthalpy of formation is minus 393.5. And then the last one, we have water. And note, water is in the gaseous state. They have different enthalpies, liquid water versus gas water. This had an enthalpy of formation of 241.8. Okay, so again, these guys, all of these values is something that you would either be given in a problem or you would have to look up on your own in the appendix. So appendix C. Okay, so now we're going to utilize them in our little enthalpy equation to calculate the enthalpy for this reaction. So I always like to keep everything organized so I don't get confused about signs, etc. So I'm going to start with the products, and I'm going to use brackets to denote that I'm summing essentially all of the products. So we have two products here. We have CO and we have water. And so for CO, there are 4 of them. So that's where the little N comes in, multiplied by their stoichiometric coefficients. So 4 times the enthalpy of formation of CO, which is 393.5. Again, the units here are kilojoules per mole. So the units are going to stay kilojoules per mole for all of them, but I'm not going to write them because I get lazy after this point. Next product is water. There are 6 of them. So water is minus 241.8. And again, I'm lazy. Note that that's kilojoules per mole. I'm going to subtract from that the enthalpies of formation of our reactants. And again, I'm going to use my little brackets here. So I have 2 of the C2H6. That had a value of minus 84.68. And then we have 7 waters, or 7 oxygens, pardon me. And then oxygen, because it is in its elemental form, has an enthalpy of formation of 0. And again, the idea behind that was like, oh, hey, it takes 0 energy to make thing in its natural and elemental form. So that's why these guys have this delta HF equals 0. Okay, so then after that, it's just keeping track of addition, subtraction, multiplication, making sure that you're not forgetting your signs. So this guy ends up being minus 1574 point nothing, so kilojoules. Note that when we multiply our stoichiometric coefficients in, it's going to cancel the moles. So long-term our units is going to be in kilojoules. Plus this guy, which is minus 1450.8. So those are my products. Now I'm going to minus my reactants. This is a minus 169.36. So we keep on with that. We've got combined for our products, we've got a minus 3024, and then plus this 169.63. So overall, long term, we get a minus 2,855, and this is in kilojoules. Okay. So this is great, right? So now we can calculate the enthalpy for any reaction as long as we have these nice little standard enthalpies of formation. So make sure you guys practice that and you watch this whenever you are going over and preparing for the exam, because I can 100% guarantee you will see something like this on the exam.